Okay, suppose you have a spectrum of electrons and energy E, and alternatively E is proportional to gamma, the Lorentz factor. There is a cursor. You see it? See the black dot?
What's alpha?
What?
What's alpha?
Alpha is...
Here, alpha.
No, this should be alpha also.
Ah. So
This was typed by somebody, and she made a lot of errors.
I remember correcting this. I remember correcting this.
You remember correcting this?
Yeah.
Well, does ARPA have your corrected version?
Should be there, but I don't know why it doesn't show up yet.
Well, maybe you didn't send them the last version.
I will check the folder and see.
Yeah. Now the question, so we know that each electron radiates energy proportional to the at a rate is proportional to the square of its energy.
Right.
So it's either minus alpha times and what is M of V? That's also a misprint.
Yeah.
No matter what I do, I can't get a break.
Okay,
you corrected this too.
Yeah.
I'll correct that. You just write in.
This MCD.
10.
Yeah. No, eta.
Yeah, it's probably an eta. Eta is just N of V times E.
Yeah.
Now the if N of V dE is proportional to e to the minus 2, then the number of electrons per unit logarithm of energy is e to the minus 1. That's all. So minus alpha plus 1 would be minus 1 instead of minus 2. Now, each one is radiating at a rate that's proportional to e squared. So so the rate at which the amount of energy that you have emitted in by any logarithmic interval is it's the emission. It's e to the minus alpha plus 3 is the rate of emission well, let's just say it's the emitted power. By electrons we'll write d log E here at say the log of the energy between log E and log E plus d log E. What?
What is this? The emitted power by electrons?
Yeah, between who's between E and E plus DE.
With energy between?
At energy. Yeah. In fact, I'll just say at energy between E and I'll just say energy between E and E plus DE, so you know what d log E means. Yeah, I'm not even sure this is right. Anyway, this is the rate of power emitted from given the energy variable, which describes the electrons. But we want to describe the amount of power emitted per unit frequency interval, and the frequency is proportional to the energy squared. So d log omega d log E is constant.
Okay.
And that's why I use logs, because the logarithm, is just linear. There's just a linear dependence, and this should be log omega, not log E. So this is the power emitted, but expressed as a function of gamma, of omega rather. This is just wrong. This is a totally uncorrected version. Let's say P, the power emitted by the electrons, d log E is equal to e to the is proportional to e to the minus alpha plus 3, right? It's out plus 1 plus another e squared. And this is d log E. So P, let's make it a slightly different P. In fact, let's make this P different, because this P is so P of omega d log omega is equal to P of E d log E, and it should also be e to the minus alpha plus 3, which what? No, it's
no, not this one, the next one.
Yeah, proportional.
E is proportional to root under omega.
D log E.
So,
D log E.
so just a second. D log E. Okay. So P of omega.
E3 minus alpha is equal to constant.
P of omega is proportional to
E3 minus
yeah, e to the minus alpha plus 3, but that's omega to the minus alpha plus 3 over 2, right?
Mm-hmm.
Yeah, okay. That's right. But this is the amount of power. I'm gonna write it this way. I'm gonna write d log omega proportional. Just to remind you that this is the amount of power per unit logarithm interval. So, for example, if alpha is equal to 2, then P of omega is proportional to omega to the 1/2. Which means at high energies you get more energy radiated. And that's assuming that the electrons don't lose their energy. See, this is generally considered to be the initial spectrum. Now, it could be that the spectrum of electrons changes because the electrons cool. That's different. So this is as long as the electrons aren't cooling. The faster ones, the more energetic electrons which radiate at higher frequencies, radiate their energy faster. Which is why, even though the amount of energy per unit logarithmic interval in electrons is constant, when alpha is equal to 2, alpha plus 1 is e to the minus 1, that's the number of electrons. But if I multiply it by the energy, I say the total energy in the electrons per unit logarithmic interval is constant when alpha is 2.
Okay.
Because this is e to the minus 1 times energy per particle is a constant. So even though the electrons in each logarithmic interval receive the same amount of energy, the more energetic ones are radiating theirs away faster, which means they'll disappear faster. And when they cool, on the times within the lifetime of the object, that's called a cooling break. And then at that point, this becomes steeper by power of by 1 extra power. And that's Now, usually people express they express things in terms of the flux for per unit frequency and not per unit log frequency, and this would be times omega to the minus 1, which is this why omega to the minus 1, because it's d log omega, which is equal to p of omega times d omega over omega. Omega is just nu over 2 pi, so I could just write this p of nu over nu e nu. So then it would be p of nu would be nu, f of nu would be nu to the minus 1/2.
Okay.
And I think we can say it's minus alpha plus 1 over 2.
Mm-hmm.
Okay. Now, when the electrons are being injected at a constant rate and they're cooling, then n of E dE is equal to e to the minus alpha below the cooling break. And why is it proportional to 1? It's equal to e to the alpha, e to the minus alpha times the lifetime of the electrons. You're injecting at a constant rate. The number you injected within one lifetime is 1 over is just proportional to the life before they cool. It's the time it takes them to radiate away their energy. So it's just times the lifetime. But what's the lifetime? The lifetime is what power of E?
So is it cooling time?
The cooling time. What's the cooling time as a function of the energy?
1 over E?
1 over E, yeah, because its rate is E squared, but it has E, so the lifetime is 1 over E. So this then becomes e to the minus alpha minus 1 dE. And then P of nu, well, let's make it let's make it P of nu d nu is then equal to what? Well, wherever I had an alpha here, I replace it by alpha plus 1. So minus alpha is minus alpha minus 1. And instead of having f of nu proportional to this should have been
minus alpha plus 1 over
sorry. This is new to the minus alpha plus 1 over 2. So here I just replace alpha with
So it's minus alpha plus minus alpha.
so it's minus alpha over 2. Actually, I want to write it like this. Never mind. Let me make this organized. Above cooling break. Okay. So f of nu is proportional to nu to the minus alpha plus 1 over 2 below the cooling break, and proportional to nu to the minus alpha over 2 above. Now, if alpha is 2, if alpha is equal to 2, so alpha f of nu is proportional to nu to the minus 1, and p, simple p of nu is p of nu d log nu is just equal to a constant times d log nu, right? Because this is the amount
Yeah, because P over nu is proportional to F. So if it goes
just a second. P of nu is proportional to f of nu times nu, right? So P of so never mind the log. P of nu is just equal to a constant, which means that the same amount of light above the cooling break is emitted for each logarithmic interval in nu. And why does that make sense? Well, because the electrons had an equal amount of energy within each logarithmic interval, and they lost it because they cooled. So you knew that the amount of radiation you got above the cooling break had to be equally distributed in logarithmic intervals. Just by the fact that the electrons were and they cooled.
So when they cool, they fall to low energy. So this will change the spectrum unless they are not confined.
When they cooled, I'm assuming that they fall to low energy.
But they are not confined to some special location.
No, if I really did it carefully, I would solve the Fokker-Planck equation carefully. I would put in a cooling term By the way, I probably should say something about the Fokker-Planck equation.
What is the equilibrium term? How does it look like?
Alright, the Fokker-Planck equation it just describes the evolution. If you want to see a rigorous definition, Chandrasekhar in 1946, I think it's in Review of Modern Physics. He wrote a review article, very rigorously deriving the Fokker-Planck. You could probably get it on Wikipedia too. But it basically describes the evolution of anything dm dt, and it's equal to, let's say it's a function of energy. It could be a function of x. Like the diffusion equation is an example of a Fokker-Planck equation. But the Fokker-Planck equation includes systematic acceleration too. So it's dde times n dE dt. This is just the flux in energy space.
Okay.
You could think of dE dt as being, if E were x, it would be a velocity, and then the density times velocity is equal to the flux. And then it's plus dde dv dde n.
What is this?
It's the diffusion coefficient in energy. So we don't even have to use this term for what we're doing. I mean, and then you can even write a term minus Rn, which is this is the escape rate. So if you really want to be technical, and you can write an injection term, which is just
What is this term again?
the injection term. It's just it's a source term. You're just adding new electrons or whatever. So even if I solve this in steady state, by the way, there's a minus here, because if they're being accelerated forward and n has a positive derivative, then then it decreases, because with time you see the stuff that was at lower energy, which is less if dNdE is positive. So this would be minus dE of n times E squared times some constant, which is the rate of synchrotron loss for a particle of energy E. So that's this term expresses synchrotron losses, and you could also put in you could say that I of E is proportional to B times e to the minus 2, because let's say that's the spectrum at which fresh shocks make new cosmic ray electrons. So this is the let's say the cosmic ray production term. Now, if you solve this equation,
you have diffusion in E in the equation before.
Yeah, but let's neglect energy diffusion, because the acceleration stopped. this was old-fashioned. This is when they were interested in second-order Fermi acceleration. And also you use it in kinetic theory. If you have Brownian collisions, you have diffusion in empty space. But just solve this equation. What do you get? If this is negligible, you get n is equal to e to the minus 2. In fact, let's just call it e to the minus alpha. And if this is significant and it balances this, then you know that n times ae squared is equal to be to the minus alpha plus 1. And I'm integrating with respect to e. So it's minus alpha plus 1. And then I divide by ae squared, right?
To get in.
To get n.
I
So
would
you would erase that one, a square.
directly pocket here.
If I put this down here. So so anyway, this is proportional to e to the minus alpha minus 1. So like I said, it just gets, but that it's just expressing what I said in words. That the lifetime is proportional to e, so 1 over e. So so there's an extra factor of 1 over e in the when the cooling term is important. All right. All that is fairly elementary. And by the way, they see radio spectra that are typically, they see electron spectra when they measure the cosmic ray spectrum that's e to the minus 2.7 or something, or e to the minus 3. And for radio spectra, they see alpha minus alpha plus 1 over 2. It comes out about right because they see spectra like 0.6, 0.7, 0.8, between 0.5 and 0.8 usually. So that corresponds to electron spectrum between 2 minus 2 and minus 2.6, and that's what you expect from the measurement of the cosmic ray spectrum. So now that's synchrotron radiation. Is it spontaneous emission or stimulated emission? Or it's also inverse Compton, which is just scattering, but you can think of it as being an emission process.
So it should be stimulated.
By what?
No, you asked if it's
Synchrotron. Let's go back to synchrotrons. It's stimulated or spontaneous emission?
synchrotron is doing things
That's
like
right.
that, right? So
You
something.
see, the formula I just derived was it's
Right.
stimulated or spontaneous emission. You said stimulated,
Right.
and I said stimulated by what?
Whatever makes it.
No.
No?
That's like the potential term in. An atom has an electric field, but when an electron emits spontaneously, you don't say that it was stimulated by the electric field of the nucleus.
Yes.
Spontaneous
because
emission
there
has a
is
definite
something
meaning.
different.
That means it was emitted even though there were no photons already there. So
Okay.
synchrotron emission, what I derived was, 2/3 a squared e squared over c cubed. That's when there's nothing else there.
Okay.
That's it. And you're accelerating the electron, but in a vacuum. So there are no other photons. So synchrotron emission is stimulated emission.
But you have magnetic field.
I have a magnetic field, but that's part of the surrounding potential. It's not a photon.
If you imagine a vacuum electric field, then you have vacuum photons.
Right, but we said, as we said last week, that's not what causes stimulated emission. The vacuum fluctuations do not cause spontaneous emission.
J nu.
What?
You told that J nu, A nu, the electric field in something. The Hamiltonian part.
Well, the thing that causes spontaneous emission is the photon that it's going to emit.
Okay.
That's what stimulates spontaneous emission, is the future photon. And how do I know that? Because it's time reversible, and the time reversible future photon is stimulated absorption, making the future photon disappear. And that's stimulated absorption by one photon if it disappeared. So synchrotron emission is spontaneous emission. The way, if there's already photons there, then it could be faster. Then stimulated emission is an instability. The more photons you get, the more stimulated emission you get, and therefore the more photons you get, and therefore the more. So it just grows exponentially.
So if you have more
If it's
photons, you have more synchrotron.
In principle, yes. So my point is that, but not necessarily, because they will also be getting absorbed. If you add more synchrotron photons, they'll be stimulating more emission, but they'll also be getting absorbed. So, when I said you get an instability, I meant if there's no self-absorption. But obviously at some point, even in instabilities, even in plasma instabilities, something has to set in. Now, it depends on the instability, but for synchrotron emission, obviously, if the emission is too bright, it exceeds the black body limit. And the spontaneous emission is opposed by stimulated absorption, right? So what temperature, if I have an electron spectrum that's a power law, what's the temperature of the emitting electrons? I mean, it's not, obviously they're not all at one temperature, but that doesn't mean that they can't self-absorb. So the definition of the kinetic temperature of electrons is when you're talking about emitting a given photon, it's just the relative populations of the two states.
Okay.
Before and after emission. So if the electron emitted a photon that had energy d epsilon, then and the energy of the photon, of course, is much less than the energy of the electron. So the difference in energy between the initial and final state is very small. So So the we call them in originally states 2 and state 1. So the number of electrons in the excited state divided by the number in the final state is just equal to dN dE no, let me say it this way. Okay, this is the I don't even need to, I'm not even going to do that. I'm just going to say the number in the final state minus the number in the initial state is just equal to minus dN dE times the energy of the photon. Right? Because it's delta n. And epsilon is very small, so I can just take the first order. Okay. So
What is this in there?
Epsilon is delta E. Energy difference.
what?
Epsilon is delta E.
Difference between
Delta E,
energy.
yeah. It's the I'll call it the epsilon gamma, so you'll know it's the energy of the photon.
Just put H omega.
Okay. H omega. Now, if I divide the fractional difference is, I divide by the number in the final state. And then this is 1 over n, right? Because it's about the same. Okay, so this is just d log n dE times h omega. But what is the temperature? From the point of what is the effective temperature in that case, if I'm talking about two states? I mean, n initial over n final is equal to e to the minus h nu over kt. Right? That's the Boltzmann factor. So NF.
Can I ask you your question?
minus ni over nf. Yeah, you can ask me a question. Just a second.
This will be 1 minus equal to.
It's 1 minus e to the minus which is equal to h omega over kt. So that means that kt is equal to
NF over NI H omega. Right?
it's equal to d log n dE.
Yeah.
Now, if n is equal to e to the minus alpha, I'm sorry, there should be a minus sign here, right?
What?
Wait a minute, wait.
Why you write NI over NF is just each from SH crossing over KT. It's also degeneracy difference.
I'm talking about two states.
Just
Talking about
check.
two states. Hello?
The ratio of
Ken?
the final state. So the
Boss?
reduction there.
כן, אני צריך כבל למסך. יש לך במקרה כבל למסך? אני לא יודע איך קוראים לזה. מה שמכניסים למסך עם כל ה... לא, אם אתה צריך את זה. איך אני מקבל עוד אחד? אני מזמין? בבית הסטודיו אפשר לקנות? אוקיי. אוקיי, בסדר, תודה. I'll get to the degeneracy in a minute. But this is just two states. So really, I'm sorry, really I should, I should talk about phase space density. So I should really call this f of e I over f of e final. And this is f of final minus f initial over f final. Now, the phase space factor, I have to, what time is it now?
3.
It's just 3? Alright,
What do you mean by just
n of e dE counts, it includes phase space factors because e is a one-dimensional variable, and it's really 4 pi f of p times p squared dp, and and this is just 4 pi over c cubed f. If assuming f is isotropic, I can just write that fp e squared dE. So if n goes to e to the minus alpha, then fv goes as e to the minus alpha minus 2. And the effective temperature emitting at E is therefore dN dE, d log n dE, which is just alpha plus 2 times E, right? Is that what I got here? Yeah, KT. Is this right?
E over plus 2.
E over alpha plus 2 or E times alpha plus 2. Did I make a mistake here? This looks right?
Yeah. E the same thing. Alpha plus 2.
My intuition told me that it should be times alpha plus 2. No, if it's steeper, it means the temperature is smaller. Yeah, okay. So it's over alpha plus 2. Yeah, okay. Alright, so that defines its effective temperature. And when the radiation temperature, the brightness temperature of the photons, which you should also know how to define, just in any given mode, it's the number of photons divided by kT is the brightness, tells you what the brightness temperature is.
What I don't understand
The kT divided by the photon energy is the number of photons expected in the mode. So if I give you the number of photons in the mode, and I give you the energy of the photons, that tells you the brightness temperature. And self-absorption sets in. Synchrotron self-absorption is a fact of life. It really happens. We see it. And it sets in when the brightness temperature of the synchrotron emission exceeded the effective temperature of the electrons that we're doing the emitting.
What's it saying?
When the brightness temperature of the emitted synchrotron photons exceeds the effective kinetic temperature of the electrons that emitted those photons.
It goes into heating.
No, it goes back into the electrons, except that the electrons were doing emitting in the first place, so it just means that you have no net emission. And so the question is, what is the spectrum? If I have a region, below which the electrons are self-absorbing, what is the spectrum there? we already did what happens above self-absorption when it's not important. It's e to the minus alpha plus 1 over 2 if it's below the cooling break, and it's minus alpha over 2 if it's above the cooling break. But all that was assuming it's optically thin. Below the synchrotron self-absorption limit, there's obviously... so you think about that for homework. We'll do it next time. And I want homework from everybody. The grades based on homework.
Okay.
Yeah. Well, you don't have to learn the course.
I wanted to ask a question regarding this. How can you use the black body radiation when, as I understand it, when you use the power alloys, the energies are way above the ranges that you can use the black body radiation?
No, I didn't use I never used black body radiation in this course. I didn't even have to say the word. All I said in the first lecture was detailed balance. Physics is always in detail time reversible, as far as we know. I mean, certainly in astrophysics, and the emission and absorption process are the same thing, time reversed, and they proceed at the same rate.
But for the body temperature, you don't use it? I mean,
I am using it.
It says in here, use the black body temperature.
That's right, but I didn't have to say black body temperature.
So what?
I could have
what
said
does
the
it tell you?
temperature at which emission and absorption are in equilibrium. And that applies to any physical system. It doesn't have to be in thermodynamic equilibrium. It's just the two states are in detailed balance. So that's it today. Next time you do that homework, and next time we'll discuss.
What is
Didn't I just say it?
your website?
It's a website, yes. It's on the website.
No, I just said it's what I just said.
Self-absorption.
So can you?
No, it's not what's on the website, because
no?
each year I give different homework.
Oh, okay.
So what is the more?
That's what.
The homework is
This is homework 2, right?
yep.
Can you write it or something?
Yeah, I'm gonna write it. What is the spectrum of synchrotron self-absorbed photons when n of e dE proportional to e to the minus alpha dE. So the electrons are power law, and we already said what their temperature is. So you just need to say what the photon spectrum looks like in this case.
Okay.
And the spectrum doesn't change with time.
We're assuming, yeah, no time dependence here.
What is the spectrum?
I could say, if it did change with time, I would just ask you at any given time. Self-absorption is an instantaneous situation.
So shall I put up in the website this homework also?
Yes.
Yeah,
No, I mean only this, right? And nothing else.
for the second homework. All right, lecture over.